Hello everyone, my name is Daniel. I should warn you in advance, I'm not a practice speaker. This is actually my second talk. So if at all I'm a little bit nervous, please forgive me. And then also, I haven't developed my style yet, so I will largely be reading from my slides, reading a lot. But okay, to get started, so I'll start with an outline. My talk is split into two parts, the practical and the theory. And I'll get into these sections as we go. So just get started right away. The first half being the practical, my introduction. So who am I? I'm a self-taught coder. I've been programming in C++ since 2005. I don't currently work in the tech industry. I have a Bachelor of Arts majoring in math, minoring in economics. I'm an Inuit person, specifically Inuvialuk from Canada's Western Arctic. I am devoted to the continued renewal of my people's language and culture. So why C++? It is a life goal of mine to build a programming language for multimedia production. I hope to offer said language as an option for telling and retelling my people's stories, traditional and new. Such a language will generally require systems level performance, and so C++ is a good fit for writing its first compiler. Okay, so what is a metacompiler? The short answer for now is it's a compile time compiler. My talk is about the working metacompiler that I have built, and this section provides my motivation for doing so. How long have I been working on this project? Directly, about 2 years. Indirectly, about 10. What would motivate me to work on this for 10 years? Loops. When I first started programming, the initial years were about getting to know the language. After that, I spent time writing in the Qt framework. Graphical programming is fun. I had some success. I even wrote some unpublished smartphone apps. But after a while, I plateaued and decided it was time to improve my skill set. What did I do? I reproduced the standard library containers such as vector. In doing so, I found myself writing many loops which I felt were both small variations of each other and tedious to write. So pseudocode of a very simple loop, while in does not equal end, perform action on in, and then increment in. Here's a small variation of that loop, while in is less than or equal to end. So in this case, once you get to the endpoint, you perform the action and increment one more time. Another small variation, once you get to the endpoint, you perform the action again, but this time you don't increment. And another small variation, before you start the loop, you increment first without performing the action. So with loops like these, I was spending more effort thinking about the syntax than the semantics of the loop. The trade-off with this syntax comes from the idea of scope. With style grammar, scope is hard-coded. This limits our options when it comes to loops. Scope is good though. If you've ever written assembly, you realize the importance of scope. So I had to find another way. Okay, so ranges are the standard solution to this problem. I designed an alternative called intervals. I borrow the interval notation from math. The idea of an interval is it encodes an iteration, but with options which communicate how the iteration algorithm acts on its endpoints. The options are defined as follows. So we have closed, opening, open, and closing. So closed acts on the left and right endpoints. Opening skips the left, acts on the right. Open skips the left, doesn't act on the right. And closing acts on the left and not on the right. Okay, and just a practical example, we can sum over the interval, closed interval between 1 and 3. So we include the endpoints, so that's 1 plus 2 plus 3, which is 6. Or with an opening interval, we skip the 1, so we have 2 and 3 is 5. Or open interval, we skip 1 and 3, so we're just left with 2. closing. So 1 plus 2, and then we skip the 3, so we get 3. So as for my motivation, to summarize, I wanted access to a domain-specific language within C++ itself. Okay, so what is a metacompiler? It's a compile-time compiler which compiles DSLs. In this section, I introduced my Chord DSL. It's not the point of this talk, but it does demonstrate what's possible, given a working metacompiler. Okay, so we have an example, square, start simple. So we have the program is called main. We take one variable x. Just like C++, it has the end line. We have a label called body, and the main instruction is we multiply x by x. This is assignment, but it's slightly different than C++. In this language, it also includes a function call. So there's a different notation for just assignment alone. I'll get into that momentarily. But so we multiply x by x, and we assign it to what is an anonymous variable, which is a period. And the paradigm there is you can think of it like copy and paste. So the period is copy, and the line below the underscore is paste. Okay, so next example, sum of squares. Okay, so we have main of x and y. Our body is we multiply x and x and store it back as x, multiply y by y, store it back as y, and then we add these two updated, the updated x and y to get the sum of squares. So x plus 1 squared. Okay, so main of x. In our body, we add x plus 1. We copy it. In this case, we can paste it more than once. So then we multiply what we pasted, and so we get square of x plus 1. Okay. This example is just to demonstrate that you can multiply and add and everything else more than just like 2 at a time. So yeah, main of t, and we multiply t 5 times. Okay, so square again, except I'm defining it through what I call argpos. So new grammar, we declare square. This is the assignment operator, the hash or the octothorpe. So argpos allows you to define new functions. So it says that we're defining a function that takes one input. We'll call it arg0, and it's defined by multiplying arg0 by arg0. So that ends up being square. Okay, so sum of squares. So like before, we can declare square and sum of square, and then we define square just as previously. So sum of squares is subpos, which is similar, except here we're saying we're defining a function that takes 2 input, and we add the square of the first input with the square of the second input, which it would be the sum of squares. And below in body, then we call that function on x and y, or the original x and y. Okay, so I also include curry from functional programming. So for the main instruction, we define twice. So we curry, we define a function that takes 1 input, and we multiply that input by 2. And in this case, I added a binding to demonstrate, well, the purpose of this Chord language is to be embedded in C++, so I want it to interact. So I'm just demonstrating I can bind C++ content into this language. So I can bind the value 2 to this variable 2. Okay, so naive factorial. There's a bit more here. So we'll start at the top. So type T, in C++, that would be type name T. So to find factorial of n, this time around I'm not calling it main, and then a trailing return type. So in the body, we test if n equals 0, we branch to done if that's true. Otherwise, we subtract n minus 1 and pass it to factorial. So that's factorial of n minus 1. And then pass that to multiply by n, so n times factorial of n minus 1. And then when we branch to the done label, we return 1, but making sure it's of type T. Okay, so factorial again, but with a goto. Another thing to mention is that this language is largely assembly. So I just wanted to show here, like you can call goto and loop background. Okay, so why is this language called Chord? Chord is a high-level assembly language which provides direct support for the classical functional operators. So repeat, map, fold, find, sift. In C++, I don't know if there's a repeat. There might be. But basically, with repeat, whenever you want to like fill an array with zeros, you're repeating the same operation over and over again. So that's repeat. Map would be transform, fold, accumulate, find is find, and sift, it's filter. Okay, so in particular, I modified these operators to work well with C++ iterators. I wanted a distinct terminology to describe these new grammatical patterns, and so I loosely borrowed from music terminology. I'm not a musician, so please be kind with my interpretation. I first rename an iterator to be a note. Two notes together define an interval. A sequence of intervals is a chord, and a sequence of chords is a progression. Okay, so referring back to my original motivation, I wanted to write loops with a grammar that let me focus on the semantics of the algorithm, not the syntax. Okay, so giving this sum example again, it was a sum over a closed interval between 1 and 3. So how would we implement that sum as a fold in this Chord language? Okay, so here we have the regular patterns. So we focus on the fold component. Well, there's a lot going on here, so I wanted to just break down the grammar in the simplest terms. So fold, by specifying n, you're saying fold over n inputs, or input iterators. Combine is just the binary or monoid operator of the fold. I just like to call it combine. I decided to generalize my fold to include an act, which is kind of like map, because sometimes you want to map before you fold or do them together. So normally when you fold, you're folding into a value, and you're usually making an assignment, but sometimes you want to generalize that, like for generics, so you might want a custom assignment, so you can specify it there as a mutate. And then finally, this fold, at the lower levels, it is still a loop, so we need a break-in condition. Okay, so back to this instruction or definition. In context, we are summing over in and end with the return value out. Here I'm saying the out variable is what I call a fixed iterator, which conceptually just means, like, you can conceptualize it as an iterator, but it's not actually iterating or moving, so it's just fixed. I just wanted to make that distinction in the grammar. And then otherwise, we have a closed interval in and all the way to end. And so if it's a sum, our fold is an add. And these two, So the star is dereference. So in this case, my out, I define it as a pointer or an iterator, in which case you want to dereference. And the in is a numerical range, which cannot be dereferenced. So the at is just identity, which say do nothing before you pass it to the add. Okay, and then finally, my Chord language, I designed it such that, well, every variable is const by default. So if you want to mutate it, you add the punctuation to clarify that. Okay, so another example, vector addition. Okay, so in this case, vector addition is a map. It takes 2 input iterators, and our map operator is addition. So it's like as you're iterating over the 2, you add the 2 points, and then you map it to the third, and thus you get vector addition. Okay, so change of base. I might not have time to fully explain this. I'll explain the very beginning, and at the end, if I have time, I'll return to it and go more into detail. So change of base, for example, you have number 12, base 10. You want to turn it to what is it in base 2? So from a functional perspective, you first turn it into a list. And to iterate over that list, you start with 12, and to iterate, you divide by 2 to get 6, and divide by 2 again to get 3, and again 1, and then finally 0. And then we map that list using the remainder or the modulo of 2. So 12 mod 2 is 0, 6 mod 2 is 0, 3 mod 2 is 1, and so on. And then finally, if we want to print this, we'd have to reverse the order of this list. Okay, so to implement that in my Chord language, you have an actual chord progression, because you have 2 in a row. So yeah, I won't go into the details of this one again. We'll keep going. Okay, so hustle. What is a metacompiler? It's a compile time compiler, which compiles DSLs, the key phrase being DSLs. So here I also introduce my hustle DSL, is as close to the scheme programming language that this paradigm will allow. So factorial, classic example. So here we have type T, which is the same as Chord, which is type name T. So we define factorial of n, trailing return type T. If n equals 0, return 1 of type T. Otherwise, multiply n by factorial of n minus 1. Okay, so performance. So this short section is informal. Before we commit to detailed theory in the following, I thought I'd offer some basic stats here. But a reality check. In the previous section, we introduced the hustle DSL. In C++ 17, in order to metacompile it, we actually write it like this. So there's the original program, but now it's wrapped in a string literal. Well, it's a string literal we wrap in a function, so we can pass it as a template parameter. Here's an example of it being passed and created. And there's a static assert calling the function. So our metacompiler is a compile time compiler that turns C++ string literals into C++ constexpr functions. So they can be used both at compile time and runtime. So we won't go into the details here, but a quick explanation as to how this works is that a metacompiler turns this, and notice this is the Chord language, but it's also wrapped in a string literal. So we turn this into this, which we then pass to this. and I'll go into details about that later. Which finally turns into a constexpr function. As for performance, I present you a non-trivial algorithm, the square root function, implemented using Newton's method, written in the Hustle DSL. Okay, so I'm not going to explain the details of this, but like you define square root, and within this definition, you define several other functions, and there's recursion in the mix. Okay, so before showing performance stats on this algorithm, let's observe the stats if it were re-implemented in standard C++. So here, constexpr square root iter. To define functions inside a function, I'm defining lambdas. So same deal, I just translated it as directly as I could. So the performance on that one, and here I'm really only interested in compile times, because runtime is just standard C++. So compile times, GCC is 0.1 seconds, Clang is 0.114 seconds. So that's our baseline. So back to this embedded program. So its perf is GCC compile time 0.39 seconds, Clang 0.842 seconds. Okay, so that is the first half. Second half is theory. This half of the talk is much more academic. Be warned, I introduce a lot of my own terminology. Reasoning about a metacompiler involves a lot of context switching, and so having distinct terms helps keep contextual boundaries clear. Oh.
Question, so you're targeting 17. Are you targeting 17 specifically, or have you tried this in 20? Like the string handling, for example, you could use structural types as template parameters.
To be fair, technically, I have not tried it in anything but 17, but the way it's designed, I don't see why it wouldn't be compatible. As far as I know it.
I thought it would probably be easier.
Yeah, I committed to 17 just because I want to see how far I can take it with 17. Okay. But yeah, I'm happy to switch in the future. I know 26 has a lot of really nice features, like variadic indexing that would improve things greatly. So, okay. So philosophy. Before we can engineer, we need to design. A good start is to question our terms. This section is about design and the philosophy behind the metacompiler paradigm. Okay, so to begin, a metacompiler is a compile-time compiler. C++ is a metacompiler. We've seen what a metacompiler does. We now ask what a metacompiler is. So to take a short tour of related concepts, we ask the following questions. What is a compiler? What is an interpreter? What is a transpiler? To keep things simple, a compiler takes source code and translates it into assembly. An interpreter takes source code, translates, then executes it directly. A transpiler takes source code and translates it into the source code of another language. So do these ideas apply to a metacompiler? With a compiler, yes, a metacompiler takes source code and translates it into an intermediate assembly. Interpreter, maybe a metacompiled function can be executed at compile time. And transpiler, maybe a metacompiler takes source code and does translate it into C++, but only C++. So I've called it a metacompiler. What makes it meta? The prefix comes from metaprogramming. In C++, this means compile time programming. This includes constexpr time programming, as well as template metaprogramming. As such, metacompiler requires we refine our notion of time. We ask, what is a timescape and what is a time scope? The short answer is, when observing the lifespan of a program, a timescape allows us to decompose it into time scopes. As for specific time scopes, I won't read out the details here. There's runtime, compile time, meta runtime, meta compile time, and it's all summarized here. So yeah, compile time, runtime, and then meta compile time and meta runtime were backed into compile time. So what about constexpr time? This is C++ specific. This time scope in effect represents either runtime or meta runtime. A metacompiler requires we also consider ideas of self-similarity. Why? Because in theory, we could metacompile source code from the same language that is otherwise being compiled. Given this, we ask, what is a metacircular evaluator? What is a self-hosting compiler? And what is an abstract machine? And what is a virtual machine? So a metacircular evaluator starts with an interpreted language, builds a metacircular library, builds a function called an evaluator. This evaluator simulates the language's own interpreter. This evaluator can execute source code from the same language. So a self-hosting compiler is the compiled version of a metacircular evaluator. What's the difference? An interpreter is allowed to interleave source code translation with execution. A compiler is restricted to modularizing source code translation from execution. It must translate first, only then can it execute. This creates subtle differences in their respective designs. So an abstract machine is a state machine. It performs computations by passing data through a chain of states. Such states are usually expected to have the same shape. In effect, you can consider them to be a data structure. These machines are generally given some kind of controller, sometimes source code to direct their computation. Okay, and a virtual machine, in recent literature, is an abstract machine. It has states that represent actual hardware, can be used to simulate hardware on top of actual hardware. Okay, so do these ideas apply to a metacompiler? So the metacircular evaluator, sort of, in theory, we can interleave translation and execution to interpret. Self-hosting compiler, maybe in theory we could rebuild C++ itself, but done at compile time it might not be performant enough to be worth it. Abstract machine, yes, such machines underlie the implementation design. And virtual machine, somewhat, in theory, optimized state transitions can be designed with hardware in mind. Excuse me. So what then is a metacompiler? It is a toolchain of related technologies which translate source code into assembly. In terms of the technologies that make up this chain, it is the idea of a DSL engine that is most relevant to this talk. So what is a DSL engine? Is an abstract machine which translates domain-specific languages into assembly. And to finish this section, I ask one more question. We've discussed the idea of a metacompiler more broadly, so now we specifically ask, why is C++ a metacompiler? It is a metacompiler because of its specification, C++ 17 and later. 17 has an emergence of grammar and rules to support a DSL engine, one which is also performant. Importantly, it is independent of vendor implementation. Okay, so methodology. A metacompiler as a technology is currently split into the following parts. A parser generator, DSLs each having their own lexers and parsers, a shared intermediate representation, a DSL engine which turns the IR into a constexpr C++ function. Okay, so in this section we give a brief history and overview of the theoretical methods needed to implement the various components that make up a metacompiler. As for the DSL engine, the actual implementation details will be given in the next section. So why talk about methods? A general purpose DSL engine needs to be able to metacompile any language. And so we need its implementation design to be based on expressive theoretical foundations. We start with the methods of compiler theory, which is divided into the front end and back end. So the front end focuses on the lexing and parsing of source code. The back end focuses on multi-layered translations from an initial IR assembly to the final target assembly. Okay, so lexing, to keep things simple, lexers read source code, translate words into tokens, are constructed from regular languages and regular automata. Okay, so parsing, to keep things simple, parsers read tokenized source code, confirm sentence structure, translate sentences into IR assembly, and are constructed from context-free grammars and push-down automata. As for backend methods, assembly languages are generally implemented using methods derived from register machines. Such methods coincide well with implementing imperative DSLs. Such methods are less effective when implementing functional DSLs. Okay, so we need methods that can implement both imperative and functional languages. To motivate such methods, let's now take a quick tour of computing history. Turing machines, so Alan Turing, equivalent to mu recursive functions, well suited for modeling theoretical properties of computable functions, less well suited for modeling practical or performant computable functions. So lambda calculus, Alonzo Church, equipotent Turing machines, well suited for modeling theoretical grammar of computable functions, less well suited on its own for modeling certain consistency semantics of computable functions. Okay, so the Lisp programming language. John McCarthy, influenced by the lambda calculus, is now a family of languages including Common Lisp, Scheme, Clojure, and Racket. Well, others as well. Aligns well with the functional programming paradigm. So to delve further into functional programming, we need to equip the lambda calculus or Lisp with a type theory. But first, a bit more background. Set theory, Georg Cantor, foundational language of math, proof there are different sizes of infinity. If taken as a naive theory, it leads to contradictions. Okay, so type theory from a math perspective, Bertrand Russell and Alfred North Whitehead, Principia Mathematica, intended as an alternative to set theory. Mathematicians did not adopt this approach, instead vying for axiomatic set theory. But it did help advance the subject of symbolic logic. Okay, so type theory from a computing perspective, multiple contributors over the years. More recently, per Martin Loff, late 1900s, well suited for modeling certain consistency semantics of computable functions, aligns well with the lambda calculus, functional programming, and the family of Lisps. It should be noted, although my current Chord and Hustle DSLs do not have their own type systems, for the most part, we don't want to restrict other DSLs from this possibility, and so we need to design for type theory as well. The important realization here is that if you equip the lambda calculus or Lisp with a given type theory, you get a modern functional language such as Haskell. So type theory or not, this leads us to abstract machines. We previously introduced this idea, but in the context of the lambda calculus and Lisp, we can specifically mention SECD, CESK, and Crinoline machines. I won't go into their details, I'm just referencing them here. So each uses different grammatical artifacts from the untyped lambda calculus to implement its own version of an abstract machine. Okay, so abstract machines versus register machines. With abstract machines, they consist of some sort of version of a controller, memory lookup, and call stack. They transition states by updating these components, which is how they perform their computations. As for register machines, they are abstract machines. The only difference is their design more closely resembles actual computer architecture. So a final method worth mentioning, continuation passing style, a variation on the idea of a function where instead of returning a value, it is passed as the input to another continuation passing function. So CPS is theoretically sound and even has its own form of composition. This is my own way of explaining it. I'm not actually going to explain it here, I just wanted to reference it. Okay, so as for my library, so in this section I introduce my CCTMP library. It is an open source repo on GitHub. It is not currently ready for official release. As for the library itself, it is implemented using C++17. It does not use the standard library, so it doesn't use std. It is currently split in two, a proof of concept as well as a semi-self-hosting version. So as for the proof of concept version, it is roughly 20,000 lines of code, in part because I don't use the standard library. All DSL code examples I've already shown can be metacompiled in this version. The Hustle DSL does not yet support all language features of the scheme lang for which it's based, and this is one such example. Even though it doesn't work yet. Just to make sure it would, I basically took this, I metacompiled it into the meta assembly. Like it compiled wrong, but it was close enough that I just manually tweaked those few parts, and then I ran it, and it ran exactly as expected. Okay, so what about the semi-self-hosting version? What is semi-self-hosting? One of the long-term goals of this metacompiler is to use the Chord and Hustle DSLs to implement parts of the metacompiler itself. As this is not proper self-hosting, I prefix it with semi to make the distinction. As for the semi-self-hosting version, it is a restructuring of the proof of concept version. The first 4,000 lines of code represents the bare minimum actual C++ needed to run meta-assembly programs. Beyond these two versions, this library is split up into the front-end and back-end components. Although the front-end comes first in the translation process, it is the back-end which shapes the overall design. As such, we'll discuss it first. So the backend is designed as an abstract machine, transitioning from state to state. Each state holds some version of a controller, memory lookup, and call stack. The thing is, we don't want to run this as an we don't want to run this abstract machine as an interpreter. The trick, in fact, is that we use continuation passing functions to represent our machine states. The twist, instead of continuation passing, we're continuation constructing. We're using continuation passing composition to construct our function, which is what we want from a compiler. The backend then consists of continuation constructing machines. That's it. To date, there are 56 distinct machines making up roughly 1,500 lines of code. Each machine is an indexed function template. And just a quick note, CCTMP stands for Continuation Constructing TMP. Okay, so as for how these machines are implemented, so we have this showed previously. There's a lot going on here. So to start, we have our function template. It's always named result. It takes a variadic pack. It's constexpr, and its machine parameters are CILTR. So to make it indexed, we wrap it in a struct, which is partially specialized. So this particular one has the name goto and the note identity. So for our function template, as for its body, because it's continuation constructing, we call the next continuation. So the machine template, the machine result, and so like this doesn't look like regular C++. It's actually C preprocessor macro. Basically, the call is just really long-winded in terms of the grammar, so I just condensed it to focus on the main variables. Okay, and then otherwise, this function has its own unique instruction, which is associated with the indexing. Okay, so what about the controller, memory lookup, and call stack? The controller is passed along as a template parameter. The memory lookup is passed along the variadic pack, and call stack is also passed along the variadic pack. Okay, so this is our function again. So that's the controller where it enters and exits. That's the variable c. The I is the index where we currently are at the controller. And then there's the variadic pack where we pass the call stack and memory lookup. So as for the controller, it is a program composed of meta assembly. It is implemented as an array of instructions. Each instruction is an array of unsigned integers. What does this assembly look like? We saw it once before. It looks like this. So the first two columns, the M, N, and the MT, so those are the names and those are the notes. They're otherwise just numbers, just enumerations. So as for the memory lookup and call stack, within the context of a variadic pack and for clarity, I use the term universe for the memory lookup and the term stage for the call stack. As for the universe, it is implemented using the left side of the variadic pack. New values are inserted at the end of the left side. Okay, so as for the stage, it is implemented using the right side of the variadic pack. New values are pushed to the back, and argument order is preserved when applying functions to their values. Okay, so that's the back end. We now go to the front end. So Metacompiler front end, the component design and implementation is inspired by the Dragon Book. A constexpr LL1 parser generator is used to construct transition tables for DSL context-free grammars. The parser generator is designed analogous to the DSLs where you take a string literal as input. So this is an example. It's just the very beginning. If you read through this, you'd be scrolling down pages because it's actual context-free grammar. Okay, so as for a lexer generator, it's not yet supported. It's on my list of things to do. Currently, each DSL hand codes its own lexer based on automata theory. Okay, so next we need to discuss how we map DSL source code variables onto continuation constructing universes. I borrow the design from the classic SICP textbook, which teaches how to build a metacircular evaluator. It uses what's called an environment to keep track of its variables. An environment is an associative array where each environment is a list of frames. Each frame is a list of bindings. Each binding is a variable value pair. In our case, when we parse the source code of a DSL, every time we encounter a variable, we assign it an index within the universe. This works as long as we also have a stack to keep record of locally defined universe stage indices during function calls. With that in mind, we have the following illustration. So we would start with the initial frame of the environment. We'd add a binding, add a new binding. We'd make a function call, in which case we'd add a new frame. And then within that context, might add a new binding. And once the call is finished, we'd return to the original environment. And then maybe make another function call, and another, and so on and so on, and so forth. Okay, so to summarize the parsing of variables, the Metacompiler front end uses a SICP style environment to keep track of variables. Instead of keeping track of values, it holds an index, a promise of where those values will eventually be in the continuation constructing universe. This is why the meta-assembly controller consists of numerical content only. Okay, so before we finish this section, we have two final technical issues to address, which are of fundamental importance. Recursion and well-definedness. As for recursion, because of how we index variables, we actually know the history of a given universe. Anything further right in the universe was defined later in the program. Mutability can complicate this, but otherwise, when we define a function, even a recursive one, we only need the left side of the universe at the time the function was defined. When we apply a function call, we must provide that left side universe along with the function arguments. Even though our Functions are continuation passing. They are still functions. If we call the same function template with the same type input, the C++ compiler will recognize it as a recursive call and so complete the function. This is why recursion works within this paradigm. As for well-definedness, we need to be sure that each meta-assembly controller which compiles also corresponds to exactly one abstract machine. This is a question of consistency or of ambiguity. When we move to the next continuation, does it correspond with the next instruction? The only time this might not happen is when the C++ compiler itself recognizes a recursive call. That the coder didn't intend. In that case, this is our state machine. These are steps as we go through it. We're at step n-1, and we think we're moving to the next step n, like our controller is saying that. But when in fact the compiler creates a recursive call and moves us back to step 0. Because of this, we actually know that step n and step 0 are the same, but we have no way of knowing if the following two steps align or match. So if we had intended a recursive call, then these paths line up and there's no problem. If not, there are no worries. In this case, this case doesn't show up in practice. As our metacompiler continuation constructs, it moves forward along the controller and so calls the next function template with an entirely new controller index. Two C++ functions are considered different if they have different template parameters. Is it possible to move backward in the controller? Yes, but that requires an explicit jump instruction. The Chord and Hustle DSLs require the user explicitly request a jump as a goto, a branch, or a recursive call. So finally, there is still the possibility that the user asks for a goto or branch, but the C++ compiler recognizes it as a recursive call. In this case, the compiler also requires the return type of the function being defined, since our continuation machines use auto-deduction. As we did not explicitly provide that information, the C++ compiler will then halt with its own error message. Okay, so entailment. So this metacompiler paradigm has now been properly introduced. There are several consequences worth discussing, but as this talk winds down, I will instead leave you with what I hope is a thought-provoking idea. It is safe to say that C++ has problems as of late. So ABI, safety, successor languages. C++ also has also become so successful that it now has an oversaturated grammar space. This metacompiler paradigm with its DSL engine can help mitigate these problems. So I come from a pure math background and have spent a lot of time on foundational languages. Foundations are all about design, and after spending time on programming language design, I'm willing to say that math has things to learn from software engineering, but that software engineering has a few things it can learn from pure math. So math, like computing, has many domain-specific languages. It's not so concerned with performance, but it doesn't have interoperability concerns between languages either. The reason for this is that math has already found ways to mitigate its consistency problems. It chooses to seek out foundational languages, such as set theory, to implement all other languages. The fact that C++ can effectively model all other programming languages means it is a foundational language of computing. Any C++ successor language should directly support this metaprogramming paradigm. Why? If it's truly a successor lang, it will eventually have the same grammar oversaturation problem. Oversaturation comes from many communities using the language, each with their own overlapping but distinct domains of interest. A metacompiler successor lane can mitigate oversaturation with a DSL engine. Such a lane can certainly still mitigate safety concerns with type checkers and borrow checkers, but it can also mitigate safety with well-designed and standardized DSLs, especially if it already provides that support. Okay, that is the end. Thank you. Any questions?
Did I understand correctly that the variable binding in the environment follows the lexical scope of the program? Did I understand that correctly? And if that's the case, do you support closures?
Yes. That example I gave with the square root function, if you look at the code, I want to bring it up, but it's really buried in my slides. If you look, there are closures there, and it actually works. So like I have effectively able to do closures without introducing lambdas, which I found really interesting. I wasn't actually expecting that at first.
Since C++ has an oversaturated grammar space, can you speak a little bit to what that means practically for software engineers?
I'll be honest, that's not my area of expertise, but watching a lot of conference talks and spending a lot of time on C++, I know a lot of different communities like have their own like what they want to do with the language and the grammar they want to introduce, and like you have the committees and like everyone like wants their own thing, and so like a lot doesn't get through, but every time you add more, like it goes off in their own directions, and like that sort of language is more about sociology and like human politics rather than mathematical design.
Okay, I see.
Is there any particular reason not to use standard library in your implementation?
In a future version, I probably will, but when I started this, part of it was to actually learn, so I wanted to reproduce everything myself, but then also, until I'm really comfortable with constexpr, I wanted to do it myself in case there's an issue, because like, like my compiler will give an error saying this is not a constant expression, or it'll give an error saying this standard container won't or isn't recognized as constexpr. And so by doing it on my own, I could make it work or guarantee that it worked. Okay. Any other questions? Nope.
What plans do you have to add a type system to your language? In particular, are you going mathematical or are you going hardware based?
That's tricky. So like my two existing languages, largely they don't have types, and that's interesting because they look a lot more like scripting languages, and that can be useful for all sorts of things. But I also definitely want to push the envelope with the math side. And then there's all sorts of advantages to doing like a formal type theory version. So basically I plan on getting there, but I've lots of things to do ahead of it, so it's down on the list. It'll be a while. Okay. Any other questions? Okay, thank you. And